Bird feathers and wings are even more complicated than we ever imagined. For example, did you know that bird wings are stronger from underneath than on top? So, for example, if you have a gust of wind coming from underneath, the wing can withstand a greater force than if it were to come on top. And some birds have slightly porous wings, others don't. Other birds have passive flow control devices akin to leading edge slots you find on airplanes, and some of these birds have them, others don't. And some birds have completely different ones to what I just described. Today in this podcast, we are covering these different type of wings and their different flow control devices, patterns, features, feathers. And I'm going to say that this is probably the most fascinating podcast we've done to date. In fact, I would say that if you get to the end of this podcast and you're not mind blown, then you're probably not trying hard enough. Anyway, the number of different flow control devices that we see on birds, for example, their feathers, are incredible. And at the end of this podcast, we'll also go through how these flow control devices pertain to their gliding flight, not just their flapping flight, because their gliding flight is different to their flapping flight. And interestingly, we'll see that their gliding flight is just as optimized as flapping flight, which you may not think that's the case because birds, they flap around a lot, but they also glide a lot. So these intricacies are truly mind-boggling. And to look into these things, we are looking at a paper called what is this paper called? A Review of Aerodynamics of Non-Flapping Bird Wings. And you can find this paper in the link in the description because it is open access, so you can find it freely. And this paper was written by Mohammed, Mo to his friends, Waqar, Erwin, and Ashraf. And I think our new friends here put it best when they said, wings specifically have been the most inspirational elements. They have indeed been the most inspirational elements, from Daedalus and Icarus to Leonardo of Vinci. Actually, on the latter point, the story about Leonardo trying to come up with a way to fly is pretty funny. So apparently, back in the day when Leo was designing and building wings for humans, to test them, he wouldn't strap them to himself. Instead, he would strap them to one of his research assistants, and then his research assistant would run off a cliff and try to flap. Ultimately, this research assistant fell and broke his back. So Leo just decided to strap some new designs to a new assistant and got him to do the same thing. I don't know how this story ended, but it was a good one nonetheless. Anyway, back onto birds. So bird wings are way more complicated than what they might seem. So in figure 1 here, which I'm showing, we see a bunch of different zones from the outer and inner primary coverts to the secondary coverts. So we have primary ones here, secondary ones coming in here. And in other words, you know the typical long bird feathers that you find, like if you see a feather on the ground, you're usually quite excited about it, that kind of feather. Well, according to this figure, a pigeon has 21 of them on each wing. Blackjack. Anyway, as they divide them into the inner and outer sections, then there are these secondary feathers that are closer to the pigeon's shoulder, so these ones just here, and they're much finer and like lot fluffier. And you might think that feathers are pretty self-explanatory. I mean, you have a central shaft and strands coming off from each side. That might be true, but there are a couple of incredible design features, actually more than a couple. And the first is that, as shown in figure 4 down here, the way each strand locks into its neighbors through its little barbs that catch onto the neighboring strands of the same feather, kind of like Velcro. So if you have the central shaft, then you have these little hairs coming out on each side. Each one of these hairs has these little barbs coming off, and then they interlock with their neighbors to make the feather strong. That's why, like, when you have a feather and you like kind of pull it a little bit and then it breaks apart and you can't put it back together because these little barbs are not going together like Velcro anymore. You have to like try to find the right way to put it together. Now, the angle of these barbs makes the feather more resistant to aerodynamic forces from the underside of the body than from the top, as we mentioned, but it's these barbs that make this so. So the wing in general is stronger from underneath than on top because of these angled barbs. Then there is also the fact that the feather isn't symmetrical about the central shaft. The strands coming off one side, so we can see here, this side here, are shorter than on the other side, and that makes the outer and inner parts of the central shaft. These parts are called the outer and inner veins respectively, so the outer one and the inner ones. And the reason why one side is much shorter than the other is that this side, the shorter one, locks into the upstream feather by slotting underneath it and making the lower surface of the wings. The longer side makes the upper surface of the pigeon's wings. And the feathers that make up the leading edge of the wings are stronger than the ones downstream of the leading edge. So that's pretty cool. So these ones up here are naturally stronger than the ones down here. And you can see they're longer, probably a bit beefier. So things get even more weird when we look at some regions called the alula, which is just located right here. And also the covert feather receptors and secondary feather receptors, which are located just around generally the bird wing. The alula is this little finger, effectively, that is located around the midspan at the leading edge. And you have definitely seen them before, but probably not in the situation you expected. So the next time you eat chicken, or the chicken wings, look at the outermost part of the wing, and you should see this little additional bit poking out. That is the chicken's alula. So some researchers have said that these act like leading edge slots, which allow fresher flow to come in and produce more lift over the wing. So it allows the flow to stay attached longer, and then you can produce more lift that way. These researchers didn't say that here. Instead, they said that this alula thing is used for a couple of purposes. The first is as a strake. So a strake is something that pokes out and guides the flow. And depending on who you talk to, they can also be objects that create vortices that travel downstream and re-energize the flow, like leading edge extensions. But there is one more function these alulas carry out, and that is to sense the airflow, which then tells the bird what angle of attack it's flying at and whether it's going to stall or not. So it's effectively an inbuilt sensor for these birds. In addition to that, the alula, the inner feathers near the bird's body act in a similar fashion in that they help the bird determine whether it's going to stall or not by being very sensitive to the airflow conditions. So you can see all these feathers and features on regular birds when they're flapping their wings around, and like how they flap them around and they like slap each other in the face with them. Now, bird wings have quite a high drag and nothing you write home raving about. But, so the typical bird wing goes from a drag coefficient of 0.03, which is pretty good, to 0.13, which is pretty bad. And the 0.13 is a lot higher than what our wings are like, so like the wings that humans make on airplanes. 0.03 on the other hand is about comparable, maybe a little bit more. But there's one really cool thing. So despite this relatively high drag to begin with, the drag coefficient is almost constant across the lift production regime. So if you have the bird wing producing a lot of lift, you get the same amount of drag as if you were to produce little lift. So the bird wing is incredibly robust in that sense. And that kind of makes sense because rarely birds will cruise for long distances. So I mean, like, we all know those birds that fly like hundreds and thousands of kilometers during migrations, but these birds are a select few. Most birds don't really fly that far. So for example, the average pigeon, like average bird like pigeons, they don't really fly that far really. In reality, they only really fly if they see someone feeding other pigeons or a pigeon they want to mate with. Both of these things mean that the pigeons fly a lot within its field of vision. And what that means is that pigeons, like many other birds, take off, fly around a little bit, and then land when they find something nice. So these maneuvers mean that being highly adept at cruising at the expense of other aerial maneuvers, like taking off and landing, would be a waste and actually potentially make them less efficient. So having a high drag, in my opinion, makes sense and isn't a deal breaker because you have good amount of lift being produced with still high drag, which our airfoils do. It's just that lower levels of lift that the drag is quite high. And in fact, evolution has shown us that this approach is obviously better for most birds, otherwise they wouldn't have propagated forward. Now, one really cool thing is that apparently barn owls have thicker wings than pigeons. These thicker wings allow the owls to fly at lower speeds, while the thinner wings of the pigeons mean that they have to flap faster to produce just enough lift to get around. So it makes sense that owls would have thicker wings to fly slower, and that is because they are birds of prey. So they need to slow down to catch their prey before shooting off again. Pigeons, on the other hand, really only slow down to land. So depending on what their functions are, their wings are developed for these different purposes. So in addition to having thicker wings, the feathers on our wings absorb noise very well, which means that they are almost silent when flying. But as we all know, at least I hope we all know, birds have bodies as well. They're not just wings flying around, but these wings are there to transport the tasty, meaty center bit around. And apparently, as a bird's mass increases, so does its drag coefficient. So I'm not sure if that trend holds between two different species, but within a single species, if the bird gets bigger, like this body gets bigger, the drag coefficient also gets bigger. Not just the drag, but the drag coefficient as well. So for example, a waterfowl bird, some researchers tested these birds and then they found that the drag coefficient of just the body ranged from 0.25 to 0.39, which is quite high for a drag coefficient. That's like about the same as a regular car. And this is definitely higher than the wings in general, which we found before was 0.03 to 0.13. Now, this part the authors say next, I don't agree with very much. The first part is okay, and I mean that they say that as the dihedral angle of the wings increase, the lift coefficient drops dramatically. And that makes sense because dihedral refers to how much the wings are pointed up. And to give you an idea, just think of a time you saw a pigeon sinking down to the land. Have you ever seen like these pigeons when they're flying and they come down? They usually put their wings in this V shape upwards, so their body is below their wingtips by a long way, and then they just like sort of glide down like a leaf, kind of just gently falling down. This is dihedral because the wings are higher than the body. It makes sense that the lift coefficient drops because the effective angle of attack of the wing drops as well. And a way of imagining this is to think of a regular wing, just a flat regular wing, not flapping and stationary. Now, to increase angle of attack, you just pitch the wing up, right? So by doing that, the angle of attack increases as well. Now, if you were to tilt the wing up so that now it had a dihedral angle, in other words, you rotate it about its longitudinal axis, that now means that when you rotate the wing in the pitch direction, the wing isn't being pitched in angle of attack as much because its own local axis is no longer perpendicular to the axis you rotated it about. As such, the effective angle of attack drops, which comes with the drop in lift coefficient. So the authors are right, in my opinion, to say that the increase in dihedral comes with a drop in the lift coefficient, but the next thing they say doesn't seem right to me, and that is they say that the increasing the dihedral angle results in unstable changes of the aerodynamic parameters such as roll and even yaw. Well, that is the exact opposite of what dihedral does. So dihedral, in other words, angling your wings up, makes you much more stable in the roll because of the pendulum effect, where you have the mass located below the points where the lift is being produced. Which means that in order for the entire object to roll over, you somehow need to get the center of mass above the centers of pressure, which is almost impossible under regular weather conditions. Now, for the yaw, it is possible that increasing the dihedral angle can reduce the yaw stability, but it depends on whether the center of pressure is in front or behind the axis of rotation. So this probably depends on the bird. So it is possible that the yaw can become less stable with increasing dihedral, but for the rolling moment, definitely not. In fact, the reason we actually have, by default, dihedral on airplanes, and you only ever see airplanes with anhedral under two conditions. The first is that the designers wanted to make the plane more agile, so they put an anhedral angle, which means that they point the wings down, which actually makes the airplane more unstable in the roll at the very least, and even the yaw often. The second reason why you'd have anhedral on an airplane is to give the people who are loading the plane on the ground more room to move around the fuselage. So what you do is you mount the wings higher up on the fuselage, so it's like on the shoulders kind of thing, very high up. Then you tilt the wings down so people who are working around the fuselage, they can get their cars around it, etc. Not have to worry about hitting the wings or hitting the turbines. And an example of this airplane is like the Antonov AN225, which is a plane that features this exact setup, and it kind of looks like a person with like a huge neck muscles and then huge shoulder muscles as well. And I actually should just say right now, actually, this podcast, if you're liking what you're hearing, hit the like button, and if you want to see more like this, click the subscribe or follow button, and let's move on to the rest of the podcast. So let's talk about porous wings. So it may seem strange that wings that produce lift would be porous, but it's actually quite common. So in fact, wings all let some amount of air pass through them. It just depends on the type of bird, and also apparently the velocity. So some mathematical models have shown that increasing the velocity increases the amount of air that goes through feathers, but it needs to be experimentally or at least CFD validated, because the mathematical model says, okay, that should be the case, but we haven't figured that out exactly yet. But it's potentially true where if you fly faster, more air will go through a bird's feathers. So why would you want air to pass through your feathers? There are a few possible reasons, and good reasons. The first comes from an experimental set up by a group called Mazellier and homies. They're not really homies, just et al. Maybe one day they could grow to be homies. We'll see. Anyway, these geezers found that putting flexible porous flaps on a bluff body dropped the drag by 22%. That makes sense to me because some air can go through and kind of bleed into the hardcore wake region. So the reason these people gave was for the drag reduction was that the flaps, which were flexible, could vibrate through the aerodynamic forces, which I guess has something to do with the von Karman Street or some kind of unsteady behavior. I wouldn't be surprised if also it had to do with reducing the wake size through letting some air bleed, and probably reducing the severity of the shear layer between the wake and the free stream flow. Other researchers called Yang and Spedding poked 180 holes, each with a diameter of 0.5 millimeters, on the upper surface of an Epler 387 wing, which has a moderate thickness and cambered wing. Amazingly, doing that increased the lift coefficient of the wing from 0.7 to 1.0, so like almost a 50% increase in the lift coefficient just by poking holes in the wing. And it also dropped the drag coefficient by 10% at the same time, so it made the wing far more efficient. Now, the reason given for why these improvements occurred was because there was this turbulence inside the holes. Now, they didn't go too much into that, but from what I can figure out, these are effectively then Helmholtz resonators. And a Helmholtz resonator is effectively just a cavity that has air going over it. The air inside kind of acts like a spring, where when some air goes in, some air always has to come out eventually. And this results in certain pulses and vibrations of the air, and those vibrations can control the turbulence in a flow. As such, you can modify the boundary layer with these Helmholtz resonators. So perhaps these increases in lift and drops in drag were due to this Helmholtz effect. So let's move on to the elasticity of a bird's feathers now, because this also affects its aerodynamics, and it's pretty amazing. So if you grab a feather, you can see that it is a little bendy. Not a lot, but if you apply some moments to it, it will bend a little bit. Well, apparently this elasticity helps the bird stabilize the flow and even control it during different phases of flight. It is amazing that it seems like everything on a bird was designed with an objective in mind, which I guess I shouldn't be amazed. I mean, that's evolution, but whatever. I am amazed still because there are just so many things. And some feathers have adaptive hairy flaps. And what this means is they have hairs on their feathers, and they can adapt how much they're poking up into the flow, which then turbulates the flow more or less, which then makes the flow either more resistant or less resistant to flow separation, and allows the bird to produce more lift at higher angles of attack and more extreme conditions. So these little feathers are effectively like surface roughness. They can help delay stall. So that's pretty cool. But now we come to perhaps the most important discovery of all time when it comes to bird flight and our flight, and that is bird winglets. So if you don't know what a winglet is, imagine almost any plane you've been on. In fact, there's only really one plane these days that is used in current operation which doesn't really have winglets, and that's a 787 Boeing Dreamliner. Every other plane pretty much used, other than really old 707s or 737s or whatever, they have winglets. So imagine you're on this airplane that you've flown on. Now look at its wingtips, the bit at the ends of the wings. You'll probably see some kind of vertical surface, whether that is up or down or both. That is a winglet, and birds have them too. In fact, their winglets, I would say, are way more complicated than ours. Ours are usually just vertical metal plates, either they're up, down, or both. But some birds, as I'll scroll down and show it here, some birds have these feathered wingtips where a bunch of feathers come out, so the wings don't just end there, but end with several feathers poking out, as shown here in Figure 5. And the way our winglets reduce the induced drag, which is what winglets generally do, is that they effectively block or at least greatly hinder the higher pressure flow from underneath the wing from bleeding over to the lower pressure on top of the wing. So without our winglets on our regular airplanes, the higher pressure air bleeds over and a wingtip vortex is formed. This is effectively wasted energy because it isn't doing anything for us, this vortex. We're just making it and we're not using it, so it's just energy going to waste. So winglets prevent this wingtip vortex from occurring and hence stops this energy from being wasted. Now that is one way of describing how winglets reduce drag, and in particular induced drag. It isn't mathematical, which is why I like explaining it this way, so no matter who you are, you will understand it. And this wasted energy is drag. And this drag is termed induced drag, and more accurately, lift-induced drag. This is because it comes from lift. So lift occurs because we have a difference in pressure from the bottom side to the top side of the wing, and then that is lift, and that produces this bleeding effect. So that then results in this vortex, and there are many ways of describing why this additional drag occurs. Many of them are mathematical, and this was actually the topic of my PhD, so I had the fortune of studying this exact thing for several years. So we often can use this explanation for our wingtips. For bird feathered wingtips, we can kind of use this explanation, but it's a little bit more wishy-washy because it's quite qualitative. So the qualitative explanation would be like each one of these feathers at the end produces a small vortex, and then these vortices together, summated, produce less drag, is less wasted energy than one big vortex that would come if you just had a blunt wingtip. So that's a little bit wishy-washy. So instead I'm going to explain it in a mathematical way, but I hope I'll break it down enough so that it's still easy to understand. So here goes. So the induced drag is proportional to how quickly the lift changes as you go towards the wingtip. If it changes very quickly, then the induced drag is high. If it changes slowly, then the induced drag is low. So in other words, if like just before the wingtip, you're producing quite a lot of lift, and then all of a sudden it just drops to nothing because you're at the wingtip now, you're going to have a lot more induced drag than if it gradually changes and drops from, like, let's say, the midspan. So what these feathered wingtips do is reduce the lift produced at the wingtips and spread it over several feathers. This also spreads something called the circulation. And if you don't know what the circulation is, watch our YouTube on our YouTube channel a video called Aero Fundamentals number 11. What is circulation in aerodynamics? And you'll understand what circulation is from there. And I should also mention that lift is very closely related to circulation. And in fact, through something called the Kutta-Joukowski theorem, we can accurately calculate the lift of an object through knowing its circulation. Anyway, because the lift and circulation are now distributed across a more varied surface, the rate at which these quantities change as you approach the wingtip drops. That then drops the induced drag. There is also this idea that vortices can cancel each other out. So the explanation sometimes given here is like, if you have vortices coming off of each little feather, they cancel each other out, and then that reduces the induced drag. Now, that explanation doesn't actually make sense because the energy has already been dumped into these vortices to create them. It doesn't matter whether you're annihilating them afterwards, you've already created them, so what difference does it make? So all this explanation would mean is that the wake dies out sooner, but not that less energy is being dumped into the wake. So a better way of describing this is, as I said, the circulation, which leads to these vortices, is spread out over several tips and is weaker overall, just because the lift also drops more gradually. So as I said, I like the wingtip explanation because it is much easier to understand, but in this situation, the lift and circulation explanation is a little more of an accurate description. Anyway, the insane thing about feathered wingtips is that some researchers looked at the wing of a Harris's hawk from a 0-degree angle attack to 15-degree angle attack. The Harris's hawk is a bird with this type of wingtip where you have these feathered these feathers at the end. And they found that going from 0 degrees to 15 degrees resulted in a drop in the drag coefficient by 6%. That's insane because I've never seen a wing that has a lower drag coefficient at a higher angle attack, especially going from 0 degrees to 15 degrees. So where you would go from completely floor attached to some level of separation. So even cambered wings see a slight increase in drag coefficient with increasing angle attack. So for these wings to drop in drag as angle attack increases is nuts. And I don't know why they do that. I want to know more, but there isn't any more information about it in this paper. So I might have to look elsewhere and cover it in a later podcast. So we'll stick a pin in that. I've never seen anything like this, at least what I can remember. I mean, I'm sure that you can make a wing which is bad to begin with and just say, okay, it will reduce drag when you go higher angle attack. But this is a good wing to begin with. So for that to happen, that's pretty impressive. Let's move on to gliding flight now. So one experiment on pigeons found that their lift-to-drag ratio during glide was around 10. This may not seem great because typical airliners like the Boeing 747 have lift-to-drag ratios around this value. But when you consider that gliding is quite different to the other way birds fly, which is through flapping their wings, it becomes very impressive to achieve such a high lift-to-drag ratio because the wings essentially have been optimized for two different and very different ways of flying and do so very well. They are optimized for flapping and gliding. Now, this is the general lift-to-drag ratio of 10, and some experiments have suggested that birds can actually change the lift-to-drag ratio during gliding through 3 different ways. The first is by changing their wingspan, which is literally just stretching their wings more out or less out. That makes sense. The second way is through changing their angle of attack. And the third way is by spreading their tail. And this third way is very easy to see in real life. Again, if you go around to where any pigeons hang out and watch them land, they usually flare out their tail as they come in. And some researchers have found that spreading out their tail actually increases their lift-to-drag ratio. Now, one thing this experiment didn't look at, as far as I know, is the airfoil profile, so the actual shape of the cross-section of the airfoil, whether it's like a NACA 0012 or NACA 4412 or whatever, or Epler 387. So this is important because birds can definitely change the shape of their wings, and that would definitely affect the lift-to-drag ratio. So I wouldn't be surprised if birds do alter this during their gliding to change the lift-to-drag ratio. And the final thing I want to talk about is mechanical properties of feathers. So the reason why is because they are incredible. So first of all, they are made of keratin, which is the stuff our hair is made of. And apparently the rachius, which is the central tube, can withstand high forces without cracking. So in other words, it isn't brittle, but it's not entirely ductile either. It's somewhere in between. Now, experiments show that many feathers have a modulus of elasticity of about 2.5 gigapascals. So what does this mean? Well, the modulus of elasticity is kind of what it sounds like, and it's how much something resists bending. A higher value means it is stiffer, and a value of 2.5 gigapascals is quite low. In fact, mild steel has a modulus of elasticity of about 200 gigapascals, so steel is far stiffer. But amazingly, pigeons have a much higher modulus of elasticity for their wings at 7.8 gigapascals, so like 3 times higher than the regular feather, which means that they are stiffer. And given the shape of a feather's central core, it is thicker at the root than the tip, which means that the tip can flex more than the root, which is expected because that is how we design our airplanes. So high five to nature for doing the same thing we do. Great minds think alike. But in terms of how over-engineered a bird's feather is, it's pretty impressive. So the maximum stress a feather can experience under normal operating conditions is about 15 megapascals. So that's if it's flying around, the maximum stress its feathers will feel is 15 megapascals. But a feather has a strength of about 140 megapascals, which means that the safety factor for a feather is like 7, 8, 9, 10 times higher, which means that a bird can go through far tougher conditions and not break down. That is pretty cool because, in fact, that is much higher than most aeronautical applications. In our aeronautical applications, we have like safety factors of like 1.1, 1.2, not even. So having a safety factor for something that flies of 6 to 10 is incredible. It's mind-boggling, and it's actually quite a funny story. So I remember just this story now, where I remember these students quite a few years ago. They were making a Formula SAE car, and if you're not familiar with this, it's where they literally make just like little races from scratch to like cars to race around a track and compete against each other throughout the world. And they have to design everything from like the aerodynamics to the chassis strength, everything like that. And these students, this one year, they were designing their chassis and they put a safety factor of 0.7 in. So what that meant was that the chassis was 70% of the strength it needed to be during its lap, which meant that at some point during its lap, it was probably going to break down because the stresses would be too great for the chassis to handle and it would just break. So you definitely want to have a safety factor at least 1, but the higher the better in terms of safety. But then you have the trade-off where like agility and like power and all that kind of stuff potentially drops. So that is why having a bird with a safety factor of 10 is very impressive. That's like what a building is like. So anyway, with that, we come to the end of our podcast, My Little Aeronemesis. I really love this one because of the different aspects of bird wings. And if you did too, please hit the like button because it makes us feel good. And also click the subscribe button, and because you'll most likely see episodes in the future that you really like too. And one thing I quickly want to talk about is if you want to learn OpenFOAM. So OpenFOAM is a really cool CFD software. It's completely open source. It's free, and it's very powerful. So you can literally do anything you can do in a commercial software in OpenFOAM, and even some more stuff. And we are just finishing up our course on how to use OpenFOAM, which we think is really good because OpenFOAM is completely free, and you can do like simulations of 10 million cells, 100 million cells, 1 billion cells, rotating, transient, multi-phase, deformation, whatever you like, all for free. So OpenFOAM is great, except it has quite a steep learning curve, and trying to start out is quite tough. In fact, when I tried to learn the first 2 or 3 times, I just got so confused and I didn't know what was going on, so I stopped learning. But then I finally like put in enough effort, and over that effort, I managed to learn how to do OpenFOAM properly and well. And now it's like the thing I use. I really love it. So our course jumps over that hardship and just leads you straight through, literally step by step, how to do these simulations, and literally from the beginning. So if you don't know anything, you can still learn from the very start. And I like mean from the very start of even installing the software. So that's how basic we've started from, and then we build the course up to doing DES on rotating objects by the end. So you cover a huge amount of information and situations that you can apply to real life. And it's a really good course that we are set to release on January 1st, 2024. So if you want to learn a CFD software so you don't have to pay like 10, 20, 50 grand per year just for a license to use CFD, then OpenFOAM is definitely for you. And once you learn it, it is actually way nicer to use than any software I've used in the past. And I've used all the major ones and many smaller ones. Just OpenFOAM is like way more logical, like the flow once you understand it, which is what our course helps you do. And our course makes it easy to learn this OpenFOAM software. So you can find that in the link in the description. So if you take it and have this major, and you can have this major skill under your belt, which then helps you find a job easier because future employers will see that you have this major skill and will save them time training you, money training you, and save them paying for licenses for CFD. So you become a way more attractive person to hire. And because you just have this skill that will save them so much stuff. So that is the end of this podcast, and I'll see you next podcast. Peace out, amigos.